Oh, welcome back to lecture number 2. Feels like we've been doing a lot more lectures than this, but this is only our second lecture, and that's sort of the nature of chemistry, is that time kind of drags. All right. We've been talking a lot about ions and ionic compounds. We're going to talk a little more about those in maybe today. But remember, there are two types of compounds out there. There are ionic compounds, which means the electron is transferred, and what's actually holding the elements together is nothing more than an electrostatic charge. Ionic compounds in water can undergo what's called dissociation. When ionic compounds dissociate, it's like a couple that goes to a party. They're not bound at the hips. They're allowed to go off and see their own friends. They're at the party together, but they're not stuck. The other kind of compound is called a covalent compound, where electrons are actually shared. Now, when electrons are shared, the atoms have to remain close together. They cannot dissociate. Think about people on a chain gang working on a highway. They're not able to get too far away from each other. They're stuck together. And what ends up happening is, if you have a very high difference in electronegativity, the electron is transferred. One of the elements has such a strong pull for the electrons, it literally takes it away from the other. And we end up with an ionic compound. But when their electronegativities are relatively close, the electrons are shared. We talked a little bit about how they may not be shared evenly, giving rise to polar bonds. And if you have polar bonds, you have the potential for a polar molecule, but you won't always have a polar molecule. And we might talk about that. We might not. I haven't quite decided yet. The way to help us understand ionic compounds is with something called Lewis dot structures. Now, we've done Lewis dot structures for some elements. And to be honest, Lewis dot structures of elements are not terribly useful. But Lewis dot structures are cartoons. Okay, this is the first thing I want you to understand about Lewis dot structures, is that they're just cartoons. They do not represent what the molecule actually looks like. And in some cases, they don't even really, it's rare, but sometimes they don't even really reflect the bonding of molecules. But Lewis dot structures help us to understand covalent bonding. They help us to understand bond orders. And they're like a little puzzle, is really all they are. So we're going to do some real quick, simple examples. Like hydrogen. Now, you know, I hope, what this means. The atomic symbol always tells us what the element is, 1 or 2 letters. The subscript always tells us how many there are. When I do Lewis dot structures, I like to do it this way. I write down how many of each element we have. Then I write the Lewis dot structure for that element. Now, notice hydrogen is always an exception for Lewis dot structures, because most elements want the full octet. But remember, the octet comes from filling the s and the p orbitals. Because hydrogen only has the s subshell, it only has 1 orbital, which means that it can only accommodate up to 2 electrons. And if you look on the if you look on the periodic chart, unless you're a librarian, in which case you'll look on the periodical chart, hydrogen is up there in the upper left-hand corner. It is atomic symbol 1, so it only has one valence shell electron. And remember, when you do Lewis dot structures for elements, you only use the valence shell electrons. You'll notice that hydrogen only wants one more electron. So it's a real simple thing to do. Put down one of your hydrogens, and I always like to put a little check next to it so that I know I've done one already. But we have two of them, so we need a second hydrogen. Now don't write this down. Don't put this in your notes. Now we have two hydrogens. Now, I told you not to put this in your notes because I wrote it wrong. Because now we have to pair up these electrons. We have to see how they share. So we need to share this electron with this. But notice that I put this electron on the wrong side. This is not an easy way to share. You'd have to actually wrap around and do all kinds of things. So here's your first and very important lesson about Lewis dot structures. You're allowed to relocate that electron. Now you can put it down in your notes if you want. You're allowed to erase electrons provided you put them back. All right? You can move those electrons around. And we just share like this. So our Lewis dot structure for hydrogen is just going to look like this. To make sure that you have a valid Lewis dot structure, there are two checks that we want to do. The first one is to be sure that the octet rule is filled. Well, remember, hydrogen is an exception to the octet rule. It doesn't want 8 electrons, it only wants 2. So we look at this hydrogen, and it has 2 electrons. When you're counting up the octet, the bond always counts for both elements. This hydrogen also has 2 electrons. So is the octet rule satisfied? Yes, it is. The second rule is the total number of valence shell electrons. Okay. So hydrogen only has 1 valence shell electron, but we have 2 hydrogens. So 2 times 1 gives us 2 valence shell electrons. We cannot gain, we cannot lose electrons. So the question is, do we have exactly 2 electrons in our final Lewis dot structure? Remember that the bonds always, always, always involve 2 and only 2 electrons. That's from quantum theory, remember? Any orbital can hold up to 2 electrons provided its opposite spin. So this bond indeed holds 2 electrons, and we have 2 electrons. This is a valid Lewis dot structure. Questions about that example before moving on? We're going to do a ton of these, so don't worry about it. How about something a little more involved? Everyone seems to know that oxygen is a diatomic allotrope. O2. The first 3 Lewis dot structures we're going to do are elements for a very specific reason. So we have 2 oxygens. How about a quick quiz, Kim? How many valence shell electrons does oxygen have? Do you remember how to do that?
Not at the moment.
Okay, it's pretty simple. Oxygen, notice, is a period 2 element. Okay, look at your periodic chart. And oxygen is a period 2 element. We'll start at the beginning of the period 2 and just count. How many elements in is it? So you have lithium, beryllium,
6.
boron, 6. So we have 6 electrons around the oxygen. Remember, we're allowed to start anywhere we want. For some strange reason, I personally start at the top most of the time, not always, but most of the time, and I go counterclockwise. Why is this? Personal proclivity. Do you have to start at the top? No. Do you have to go counterclockwise? No. Do you have to go clockwise? No. You can jump around up, down, left, right. I don't care. But start somewhere. And remember to put 1 electron in each of the 4 quadrants before pairing them up. So there's 1, 2, 3, 4. We're not at 6 yet, but we have 1 electron in each quadrant. So we have no choice but to begin pairing it up. Like this. Okay? How many electrons do we have? Well, we have 6 valence shell electrons. So we have 12 electrons total that we're going to need in the final Lewis dot structure. Okay?
Okay.
So put 1 of your oxygens down. Actually, I don't like the way that looks. Just looks a little sloppy. I'm going to redo it. You allowed to do that? Of course you are. Now, when I put the second one down, I know I'm going to want to form a bond. So we may as well just put this electron here. Like we expect. Don't put this in your notes yet. Okay? And we can form our bond. Actually, there are 3 checks. There were 3 checks. I forgot the third one. No free radicals. What's a free radical? It means that you have what?
By itself?
An unpaired electron. You're exactly right. So is this a valid Lewis dot structure?
No.
No, because it has unpaired electrons. What do we do about that? Well, keep in mind, this is why I told you not to write this down. Keep in mind and always, always, always remember this. Always. When you have a pair of electrons, that is a lone pair of electrons. They do not participate in bonding. Okay? Unless you happen to have an extended octet rule, which is beyond the scope of this class, lone pairs do not bond. So, do not try to form a bond between this lone pair down here and the unpaired electron. Well, what are we allowed to do?
Move your electrons where they need to be.
We can move electrons. So we can break up this lone pair. As long as we remember there are 2 electrons there and we can replace it. So this is our Lewis dot structure. One of the things that Lewis dot structures tell us is bond order. This is the mission that James Bond is on. It's the bond order.
Mm.
Bond order means, is it a double, single, double, or triple bond? We're going to talk about this in a moment. It can never be larger than a triple bond. So it's a single, a double, or triple bond. This is a single bond. This is a double bond. And it can, and we're going to see an example of this next, go up to a triple bond. So double bonds are fine. We're allowed to do that. Notice also I kind of put, instead of putting the lone pairs on the top and on the side, I kind of moved them so they're a little more diagonal.
Notice that.
Well, this is artistic license. Remember, Lewis dot structures, they're cartoons. We're allowed to put them anywhere we want. I think it looks a little bit nicer if you put them off on the corners like this, rather than one on top and one on the side, or one on top, one on the bottom, or bottom and side. You know, I like having them a little more diagonal than squaring them off. Well, am I allowed to do that? It's a cartoon. Why not? We can do that. That's fine.
Give them personality.
Absolutely. In fact, we will discover soon, well, maybe not today, but certainly by Thursday, there's actually a reason for this as well. While we're talking about it, let's go off on tangent real quick and talk about these bonds. Why are we not allowed to go beyond a triple bond? Well, do you remember what the the p orbital looks like? There are 3 p orbitals and they kind of look like dumbbells. You have one oriented along the x-axis, one oriented along the y-axis, and the third one is hard to see because it's kind of oriented along, it's coming out of the board at you, so it's kind of hard to visualize. If we think about 2 elements with a p orbital, we're going to undergo what's called hybridization. This comes from quantum theory as well. As it turns out, any wave function that solves the Schrodinger's equation, you can add those wave functions up and you still have a valid solution to Schrodinger's equation. So you can take 2 p orbitals and add them together and you get a brand new orbital, and it distorts the lobes a little bit. It distorts the lobes. So you end up with a much smaller lobe on the side and a much larger lobe in the middle. Looks like this. Our 2 electrons will occupy this. And notice that these electrons are exactly in between the 2 atoms. They occupy that space exactly in between the 2 atoms. We call this a sigma bond. It only has one component. It only has one lobe. I mean, it has the 2 little ones on the side, but those electrons are right in the middle. So think single, sigma. It's a sigma bond. It's a single bond. Okay? It's like a hot dog. It's like someone is holding a hot dog on 2 ends. That's a sigma bond. Let's do a second bond now. The second bond cannot go in between the two atoms because that space is occupied. Occupado. But we still have the p orbital in this orientation. Okay. Kim has stepped away from her computer for a moment. So when we overlap these, notice they're going to overlap in two locations. The top lobe is going to overlap and the bottom lobe is going to overlap. And you end up with an orbital that has two components, one on top, one on the bottom. This is a single bond. It just has two parts. It's a single bond, but it has two parts. We call this a pi bond. A pi bond. So it's one bond. It just happens to have two parts. A double bond, like our oxygen, will be comprised of one sigma bond and one pi bond. The first bond is always, always, always a sigma bond. The first bond is always the bond that occupies the space between the two atoms. So if you have a double bond, you have a sigma bond plus a pi bond. Okay? Think about it like this. You have a hot dog and a bun. So a double bond is single bond is just a hot dog. The double bond is the hot dog and the bun. What's a triple bond then? Well, keep in mind, it's really hard to draw. I'm not an artist. So we have three p orbitals. We have the one that is along the axis of the bond. We have one that is along the z-axis. And we have one that's along the y-axis, kind of coming out towards and away from you. Man, that is hard for me to do. I don't know why my eraser is not working very well. See, I can't even draw it. So we have one of them oriented this way. That's still a p bond, so we're still going to overlap like this. So the third bond is also a pi bond, but one of the lobes is going to be in front, like this. So here are two atoms. So one of them is going to be in front, and it's going to look like this. The other one we're not going to be able to see. It's kind of in the back. So it's in front and back. Okay. Think of this as a hot dog bun. If someone likes a lot of bread, you might have one hot dog and one bun with the bun going on top and the bottom, and one bun going in front and in back. It's still a p bond. It's still a p orb. It's still a p bond. It's still a pi bond. It's just oriented at a right angle, top and bottom, front and back. Okay. So a single bond sigma looks like this, by the way, and you know what pi looks like. Sigma bond is always, a single bond. So this hydrogen single bond here, this is just a sigma bond. Those electrons are exactly in between the two elements. A double bond is one sigma and one pi bond. It's the hot dog and the bun. Okay. So a triple bond is one sigma bond. It's always one sigma bond. But a triple bond has two pi bonds. One on top and bottom, the other front and back. Why is there nothing larger than a triple bond? Where would you put the electrons? There's nowhere left for them to go. The space in between is filled with a sigma bond. The space in front and back is filled with a pi bond. Space top and bottom is filled with the second pi bond. Okay. Just a quick comment about these bonds. Because the pi bond is oriented either in front and back or top and bottom, the pi bond is always weaker than a sigma bond. Okay? The pi bond is always weaker than a sigma bond. But, and this is a big hairy but, the strength of the bonds add. So a double bond is always stronger than a single bond, and a triple bond is always stronger than a double bond. But that's because we're adding those strengths together. The pi bond alone is weaker than the sigma. But every single one of these bonds involve two and only two electrons. No more, no less. Every bond is two electrons total. So here in our oxygen, this bond is two electrons and this bond is two electrons. There are 4 electrons total being shared, but that's being shared between 2 bonds. All right? That kind of makes some sense? A little bit? All right. So our final diatomic example, nitrogen. How many valence shell electrons around nitrogen? Right, 5.
I found it.
Got it. Yeah, nitrogen, again, first period, start at the beginning of the period, count the number of blocks over, lithium, beryllium, boron, carbon, nitrogen. 5 valence shell electrons. If you're down further, remember to skip the transition metals. So if we're looking at something like bromine, you have potassium, calcium, skip all those transition metals, skip the lanthanides, the actinides, skip everything in between. We're only looking at S and P. So after calcium, we have gallium, germanium, arsenic, selenium, and bromine. So bromine has 7 shell electrons. Well, now it's a pretty simple thing to look at this and say, oh, well, wait a minute. We need to pair up the 3 unpaired electrons, the 3 bonding electrons. So let's go ahead and just put that lone pair electron on the opposite side. Bleep, bleep, blip. So our valence, so our Lewis dot structure for nitrogen looks like this. So there's our triple bond example. Nitrogen is often considered an inert gas. It's not, it's not a noble gas. It can react, but it is so hard to get it to react. It acts like it's inert. The reason it's so hard to get it to react is because it is that triple bond. And even though the pi bonds are weaker than the sigma, the triple bond is just the strongest covalent bond there is, always, because it has 3 of them. Let's do our check. How many electrons total do we have? Well, we have 5 electrons per nitrogen. But we have 2 nitrogens, gives us 10 electrons total. Do we have 10 electrons around our final structure here? Remember, the double bond counts twice when counting the octet rule, but only once when counting the total number of electrons. We have 2, 4, 6, 8, 10 electrons. So that checks. The second thing is the octet rule. Notice that this nitrogen on the left has 2, 4, 6, 8 electrons around it. The nitrogen on the right has 2. Remember, the lone pair electrons only count for the element that it's attached to. So we have 2, 4, 6, 8. The octet rule is satisfied. And do we have free radicals? Do we have any unpaired electrons?
No.
This is a valid Lewis dot structure. Would you like to see a compound? All right, let's do something a little bit different. Had a date once with a woman who was literally an undertaker. Conversation was just death. I asked her what that lovely perfume was, and she said formaldehyde. Formaldehyde has the formula CH2O. CH2O. What is the Lewis dot structure for formaldehyde? Well, we're going to do it the exact same way. We're going to write down each element and the number of each element that we have. How many valence shell electrons around carbon?
4.
4. Hydrogen we've done before, it's just 1. Oxygen is 6. Total number of electrons? Well, let's see here. 12. 12 electrons total. Now, not actually 12 electrons total, but more specifically, 12 valence shell electrons total. So what do we start with? Well, let's begin by talking about what we leave. What don't we start with? Here's the way I like to do when I was just learning Lewis dot structures. Do enough of these, becomes second nature. You're going to look at it and say, oh, yeah, I know that Lewis dot structure. But when you're first starting out, it helps to have a little guidance. Any element that only needs 1 more electron, save those as the very last things that you add, and you'll see why in a moment. So notice that in this one, the hydrogens only need 1 more electron. We're going to save those, and we're going to put those on last. Okay?
Okay.
When you are bonding, when you're doing Lewis dot structures, by the way, let's leave that rule for a moment. So what do we start with? Well, if you have carbon, it's actually an organic compound. We're actually delving into organic chemistry here. And usually you want to start with carbon. It's not a bad idea. It's the element that we save the one that only needs one more electron for last. So let's start with the one that needs the most. So let's start with carbon. Put that on our board first. Now carbon is taken care of. Now the only thing left, aside from hydrogens, which we're holding off on, is oxygen. Where do we put it? Top, bottom, front, or back? Kim, where do you want to put it? To the left, to the right, top or bottom?
Top.
Okay, let's put it on top. Does it matter? No, it's a cartoon. It doesn't matter. Now, it does matter where we put the non-bonding electrons. We do not want to put a second electron here because we'll have a lone pair next to an unpaired electron. So let's avoid that. Always, always, always start with a single bond. Do not jump. I've had so many students get so lost because they try to use up all those unpaired electrons quickly, and they will jump at double and triple bonds without even thinking about it. And all of a sudden, they don't have enough electrons to finish the structure. Always, always, always start with a single bond. We're just going to bond it. And we're done. We're not done, but we're done with this step. Now let's step back and look at what we have. Carbon is taken care of. Oxygen is taken care of. We are down to the elements that only need one more electron, and we have two of them. All right. So before we add the hydrogens, look at our structure. We have two hydrogens that each need one electron. That means that we only want two unpaired electrons in our working structure. How many unpaired electrons do we have?
4.
4. We have too many unpaired electrons. How can we reduce the number of unpaired electrons? Multiple bonds. Now we go to multiple bonds. So let's form a double bond. Well, there's only one place to really form it. I mean, yes, we can move the electrons around if we want, but it's convenient. Let's just form a double bond here. Now, how many unpaired electrons do we have?
2.
2, which is exactly what we need to finish our Lewis dot structure. Notice what our Lewis dot structure tells us. It tells us the bond order. It tells us the carbon is bonded to oxygen in a double bond, is bonded to two hydrogens in a single bond. It tells us what's bonded to what. Carbon, oxygen, carbon, hydrogen. We do not have an oxygen-hydrogen bond. It also tells us how many lone pair electrons we have and where. The only lone pair electrons are oxygen, which has two sets of lone pair electrons. That's all Lewis dot structure tells us. The bonding of the molecule. And again, I took some artistic license and kind of redrew this with, instead of drawing the hydrogen straight out, I drew them at an angle. Let's do our checks. Is the octet rule satisfied? Well, our hydrogen has 2 electrons. Our hydrogen here has 2 electrons. Carbon has 2, 4, 6, 8 electrons. Oxygen has 2, 4, 6, 8 electrons. The octet rule is satisfied. And do we have a total of 12 electrons? 2, 4, 6, 8, 10, 12 electrons. This is a valid Lewis dot structure. Let's take 5 minutes. I will meet you back here at 10:45. And then we'll see if you have any questions before doing another example. Is that fair?
That's fair.
All right. Let me stop the share here, and we are back. We have left off with Lewis dot structures. We're going to pick up with a couple more, at least one more example. So let's do this. C2H6O. This will be very, very instructive for us to do. It's a good example. We have 2 carbons, which we now know has 4 valence shell electrons. We have 6 hydrogens, which we now know has 1 valence shell electron. By the way, I said any element that needs only 1 more electron, you can always save it as the last thing that you add. The examples we've done so far have been hydrogen, but keep in mind all of your halogens, fluorine, chlorine, bromine, iodine, those all would also fit into this category because they all have 7 electrons in the valence shell, which means they only need 1 more electron to fulfill their octet. So hydrogen is not the only example, but it's the only one that we've done so far. Oxygen. Has 6 valence shell electrons. So how many valence shell electrons total? Well, we have 2 carbons, 6 hydrogens, and 1 oxygen. So that's 8, 14, 20. Did I count that up right? Yeah, 20 valence shell electrons total. What do we save as last? Well, in this case, we're going to save the hydrogen as the last thing that we add. What do we start with? Well, when it's organic, I usually like to start with carbon. So let's throw a carbon in here. Have we used all of our carbons? No, we have not. Kim, what would you like to add next? The second carbon or the oxygen?
Oxygen?
We can add an oxygen. Don't want to pair that one up. Oxygen is now complete. We're holding off on hydrogen, so now we need to add another carbon. Kim, would you like to add the second carbon to the first carbon or to the oxygen? What do you think? I'll give you a hint. You cannot do wrong.
You can't.
No, you cannot. because whatever you choose, I'm going to do both. So which do you want to do?
Oh, well, let's just do the carbon then.
Add it to the carbon?
Yeah.
What if Kim had chosen oxygen? I'm going to do a second Lewis dot structure down here. This is exactly the same that we had before. Now, what have we not added yet?
Hydrogen.
Not added hydrogen. In the top structure, ooh, I can't do that. Just going to move this down. How many unpaired electrons do we have in our working structure? How many unpaired electrons around this structure do we have?
6.
1, 2, 3, 4, 5, 6. And we need how many?
6.
6. Well, that is fortuitous. So this gives us a Lewis dot structure. I'm going to rearrange it, just straighten it out a little bit. Looks like this. In the bottom Lewis dot structure, how many unpaired electrons do we have down here?
6.
6. Notice that sometimes when I'm just adding hydrogens, I don't bother doing the individual electrons. I just go ahead and do a line. Sounds like I'm doing cocaine, but I'm not. I just do a line and add my hydrogen. Am I allowed to straighten it out like this?
Yes.
Yes, it's a cartoon. Is the top one a valid Lewis dot structure? Well, let's look for the octet rule. We have 2, 4, 6, let's see, 8 around oxygen, 2, 4, 6, 8 around this carbon, 2, 4, 6, 8 around this carbon. Hydrogens all have 2. On the bottom, we have 2. Didn't mean to do a little dot there. Need to erase that because that means an electron. We have 2, 4, 6, 8 electrons around this carbon. This is symmetrical, so this will also have 8, 2, 4, 6, 8 electrons. So the octet rule is satisfied in both. So which one is wrong? Oh, we forgot to check the total number. We need 20 electrons total. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This must be the valid Lewis dot structure because it has 20 electrons. Let's check the bottom just to be sure. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's also a valid Lewis dot structure. What the heck is going on? Notice that the bonding is different. They are both valid Lewis dot structures. They're both valid compounds. These are called isomers. Isomers have the same formula. Both of these are C2H6O. They are both isomers of one another. And there are 2 structures. But because the bonding is different, on the top, we have 2 carbons bonded together. On the bottom, both carbons are bonded to the oxygen. So the bonding is different. Because the bonding is different, these are different compounds.
Oh.
They have different chemical properties. They have different physical properties. They're two different compounds. They just happen to have the same formula. The top, this one, is very well known. This is called ethanol. Ethanol is drinking alcohol. When someone gets an alcoholic beverage, ethanol is the active ingredient. That's what they're drinking to get that buzz, which I don't like. I've never liked being drunk. That's just who I am. I don't judge people who like to get drunk. I'm just saying I don't like it. Of course, when I do get drunk, I've been drunk a few times. Actually, I wrote a blog about the first time I was drunk. But when I do get drunk, I also make sure that I'm home, my keys are put away, I don't have to drive anywhere. I make sure that I protect the people around me. I figure if I'm drunk and I'm driving, if I kill myself, that's my own dumb fault. I don't want to hurt anybody else. So when I do decide to get drunk, rare though it be, I make sure that I'm home. Anyway, ethanol is the drinking alcohol. Down here, we have what is commonly referred to as ether. Ether. Ether was used as a general anesthetic back around World War I and World War II. A general anesthetic knocks you out. It puts you to sleep. It was, I believe, the first general anesthetic. And they stopped using it because every once in a while the hospitals would explode. It is a very volatile organic compound. It is very volatile, means it evaporates readily. Very, very flammable. And when the mix of the ether in the room becomes just right, if there's a spark, there it goes. So they don't use ether. And the other problem with ether is sometimes people would simply not wake up again. Very hard to regulate, and sometimes they'd use too much of it. These are two very different compounds, both with the formula C2H6O, ether. Isomers. All right. How comfortable are you feeling with Lewis dot structures? Would you like to see another example or not?
One more.
All right. And by the way, before we do that, I want to make a little side note here. When we were at this point, oops. When we added the second carbon, you suggested we add it to the first carbon. I put it on the bottom. I want you to notice something here. If I put it off to the side, or I'm going to put this in parentheses, if I put it on top, it would not have mattered. We would have ended up with exactly the same compound. So do be a little bit careful here about not confusing isomers with the same compound. Because in the end, we would have ended up with two carbons single bonded to each other and a carbon oxygen single bonded. If I put it in any other location, we would have had two carbons single bonded together and a carbon oxygen single bonded together. The only thing that Lewis dot structure tells us is the bonding. So if you have the same bonding, you have the same molecule. It doesn't matter where you put that second carbon. you would have ended up with the same molecule. The only way we got a different molecule was by changing the bonding. Instead of bonding two carbons, we bonded the carbon to the oxygen.
Okay.
Okay?
Yep.
Okay. Okay, I'm trying to figure out what I want to do. C2OCl4. I think that's fair. I think we can do that. So once again, we make our guide. How many valence shell electrons in chlorine? Actually, let's not do chlorine. Let's do bromine. How many valence shell electrons in bromine?
Is it 7?
It is 7. Why? Because you skip over those transition metals. You only count in the S block and the P block. You are absolutely correct. What should we add last? What only needs one more electron to fulfill that octet?
Bromine?
Bromine is the last thing we're going to add. So where do you want to start with?
Carbon?
Start with carbon. By the way, unless you are instructed to do otherwise, avoid, when you're building these Lewis dot structures, always avoid putting two atoms of the same type together. Okay? The only exception to that rule is carbon. And here's why. For some reason, if you have two elements of the same type with a single bond between them, that bond is usually very weak. And that makes that compound very unstable. The only exception to that rule is carbon. This is why organic chemistry is such a huge field, because the carbon-carbon single bond is roughly the same strength as a single bond between carbon and any other element. So carbon wants to be bonded to itself. It's a very arrogant element. It loves itself. But let's take, for example, the oxygen-oxygen single bond. There are known compounds with oxygen-oxygen single bonds. We call these ethers. No, not ethers. Sorry about that. Peroxides. We call them peroxides. Peroxides have oxygen-oxygen single bonds. The peroxide you may be familiar with is hydrogen peroxide, which we use to disinfect wounds. And if you've ever put hydrogen peroxide on a wound, you see it's fizzing just like crazy. It's because your body has a natural enzyme that breaks down any peroxide it finds. And that peroxide is giving off oxygen. You can buy hydrogen peroxide in the store. But just about every other peroxide known is a shock-sensitive explosive. If you tap it, it will explode. Just about every other peroxide, including one that you can get for your face, benzoyl peroxide, also a shock-sensitive explosive. But they stabilize it by putting such a very small amount in a lot of cream. So there's not enough of it there to really explode. But peroxides are so unstable. And the reason they're unstable is because of that oxygen-oxygen single bond. That oxygen-oxygen single bond is so weak, it is happy to just break and form products with anything else around it. So boom, it just explodes. Ether. Farmers used to use ether to get their tractors started. And the problem with this is that ether, which is a liquid, they will often have it in a jar near a window exposed to light, exposed to the sun. Ether, when it's exposed to sunlight, will form peroxides, will form solid crystalline peroxides, usually around the rim of the bottle. And sometimes you'll still see these ethers in jars in old barns. And if you see one, call the frickin' bomb squad. Because those peroxides are shock-sensitive explosives, and it is not uncommon that a farmer will take an old bottle of ether and crack open that lid, set off the peroxides, causing a spark that will cause the entire jar to explode. Many people have been killed this way. Peroxides are very unstable. So when you're writing Lewis dot structures, unless you're specifically told otherwise, I mean, if you're told it's a peroxide, then yes, you're going to put an oxygen-oxygen single bond. But without special instructions, never put single bonds between two elements except for carbon. So Kim, we have added the first carbon here. Would you like to add? Oh, no, I'm going to do the next one. Let's add the second carbon. There's a reason I'm doing this. We're going to add the second carbon, and we know that carbon-carbon loves to be bonded to itself. It's so arrogant, I swear. Now we're saving the bromine, so we need to add the oxygen. Doesn't matter where we add it, to the left one, to the right one, doesn't matter. Top, bottom, to the side, doesn't matter. Because it's just a cartoon. It's all going to be carbon-carbon, single bond, carbon, oxygen, single bond. So wherever we put it, doesn't matter. Okay. Now, okay, I just checked. I did it right. Yay! Wasn't sure I did. Nonetheless, we've added everything except bromine. We've not added the bromine because it's the last thing we want to add. We have 4 bromines. How many unpaired electrons do we need to put our bromines on here? Remember, we're holding it off because bromine only needs 1 more electron. So how many unpaired electrons do we need?
Well, you only need 1, right?
Oh, yes, except for each bromine only needs 1. We have 4 bromines, so how many unpaired?
In the bromine?
How many total unpaired electrons do we need in our working structure here?
Well, there's 6 above, isn't there?
But we only need how many?
1.
Nope. We have 4 of them. 4 times 1 means we need 4 unpaired electrons.
Oh,
6 unpaired electrons. What do we do?
we need to start pairing them up.
Now we go to multiple bonds. So we have 2 of the same. Now here's a mistake students often make. Do not write this down. So students will say, well, we can double bond here, and we can double bond here. We immediately start trying to get rid of those unpaired electrons, but what's the problem? Now we still need 4 unpaired electrons, but we only have 2. So always start with single bonds, then go to double bonds. You do not add a triple bond unless you know you need it. So where should I put our double bond? Where do you want to put it, Kim?
Are you looking at the bottom one or the top one?
Bottom and the top are the same, which means that I'm expecting to be able to put it in 2 different locations.
Oh,
So where do you want to put it? Between the carbons or carbon and oxygen?
carbon and oxygen?
Okay, you want to put it here. I think you're wrong because
Okay.
you're a girl. I'm going to put it between the 2 carbons. I'm actually working with a student, a very shy friend of mine, works with me at the drive-in. I'm trying every once in a while, I'll say to her, well, you're just a girl. And I'm doing that because I'm trying to teach her to speak up and say, look, I am valid. I'm intelligent. I have good ideas. Okay. So anytime anyone says, well, you're just a girl. No.
Just ignore them then.
Or knock them down a peg. Now we need 4 bromines. And look, we have 4 unpaired electrons. So yours won't work. Oh, wait. I could add 4 bromines to yours. So mine won't work. Are these Lewis dot structures valid? Which one does not work?
There's nothing left unpaired, is there?
There's nothing left unpaired. Is the octet rule satisfied on both?
You already know the answer.
Of course I do.
Yes.
Yeah, absolutely. The octet rule is satisfied in both. Do we have 42 electrons in both?
Should be.
Instead of letting you count them up, yes, we have 42 electrons. I'll let you double check that. But get in the habit of doing those 3 checks. No unpaired electrons, full octet, and the total number of electrons are accounted for. What do we have here? We have 2 what? Same formula, different.
Isomers.
There are compounds that combine covalent and ionic bonds. We have a class of ions called polyatomic ions. Okay. Polyatomic ions have picked up or lost electrons, but are covalently bonded to each other. These are special ions, and professors will sometimes give a list. I've seen lists as long as 20 plus polyatomic ions, and they ask the students to memorize the names, the formulas, and the charges. I'm going to give you a few that I think you should know. So, for example, the nitrate polyatomic ion has the formula NO3 with a -1 charge. I love nitrates. They're always cheaper than day rates. Nitrates are strong oxidizing agents, which means they make things burn. Nitrites, you will see actually if you drink wine, you'll see in the bottom, in the bottle, there's a little caution there that says contains nitrites. Nitrite, NO2 with a -1 charge. Notice that we have different names. The lettering is just one letter off, nitrate or nitrite. But the formula is different, 3 oxygens to 2 oxygens. Carbonate. These are things that you might come across in everyday life. CO3 with a -2 charge. Let's see, phosphate. PO4 with a -3 charge. Ammonium. NH4 with a +1 charge. Now let's throw in sulfate. Actually, let's do another quick sulfite. And the list goes on. When you're dealing with polyatomic ions, you treat them just like simple ions. But as you recall, every example we've had, we've changed the ending of the name of the anion, typically from "ide" to "ide." So chlorine became chloride. Fluorine becomes fluoride. In polyatomic ions, the ending does not change. You use the name as it is, which is how you can recognize when you have a polyatomic ion. If it's not an ITE ending, what the hell do I have on my chin? It's not an ITE ending, it is a polyatomic ion, and you treat them just like any other ion. You do your cross trick. sodium nitrite. Okay, so it's not an IDE. Therefore, it's not a simple ion. And you just have to memorize, oh, nitrite, that's NO2 minus. So what would be the name of this compound? Well, what's the name of Ca?
Calcium.
Calcium. And CO3 is? Where do you find calcium carbonate? I bet you have it at home. There's a good chance you have it at home. What is it?
Tums.
It's an antacid. It's the active ingredient in many popular antacids. It is also chalk. Back when I used to teach and we had actual chalkboards, I would eat a little piece of white chalk just to prove to students it just thumbs.
Okay.
It's not smart. Don't do it. The difference between white chalk and Tums is that Tums is actually carefully measured. You can have too much antacid and cause what's called alkalosis, which can be deadly. But we're out of time. I have held you over a minute too late. We're going to do a few more examples of polyatomic ions Thursday. And then we're going to go into molecular shapes. Do you have any last minute questions before we go?
No.
Okay, I hope you have a great day, and I